So thank you very much for the opportunity to speak here, and very exciting occasion for me. Speaking at Dani's conference. So I want to talk about bounded orbits of diagonal flows on the space of lattices, and it's based on joint work in progress with Beresnevich, with Victor Beresnevich, Andrew Velani, and Layan. Which is not published, but what I mean is that there are some things that I understand better now after we started working on this project. So nowadays it becomes almost impossible to talk about bounded orbits of diagonal flows without mentioning the Dani correspondence. So let me start with this. So definition. Okay, a matrix X n times n matrix is badly approximable. If there exists some constant bigger than 0, such that for every vector p in Z m and any vector q in Zn and on 0, x times q plus p in absolute value to the power m times the absolute value, the norm of q to the power n is bigger than this constant. Okay, so for example, if m equals n equals 1, then this is just the usual definition of badly approximable numbers, which is x times q plus p times q is bigger. So x plus q over q is bigger than c over q. And what is the relation to bounded orbits of diagonal flows? So that is an instance of Dani correspondence. So let me define these flows. So, LP this matrix e to the minus e to the 1 over n p, e to the 1 over n and p, and e to the minus 1 over n minus 1 over n. And then ux is this matrix I x I. So this is m times n times n. Then x is badly approximable, so that's Theorem of Dani. 85. saying that X is badly approximable. If and only if there exists an epsilon bigger than 0, such that what am I saying? Such that the orbit of the lattice that is spanned by the columns of X this set when t is bigger than 0 bounded. I don't need that. Epsilon was there for different. Thank you. Okay, so how to prove this? This follows from this. It follows from model compactness criterion. Now we need the epsilon, so a set is bounded, so subset of SLM plus N R over SLM plus N Z is bounded. If and only if there exists an epsilon such that this set B is contained in this compact set K epsilon, which is defined by all those lattices, all those, let me denote it this way, all the lattices for every vector, for every integer vector, 0, G times V is bigger than epsilon. So let me show you the proof of this. That is the definition of K. So let's say, let's do, I guess, this direction. So if there is a short vector, okay, let me put here. So let's say there is a short vector in the orbit. So let's say if AT UX V is smaller than epsilon, then what does it mean? Let me just write it in coordinates. So it means that e to the minus t over one over t times x. Okay, let me call this vector pq. So in the usual way. So p is an m times m, an m vector, and q is an n vector. So I can multiply x with q to have x. And this is smaller than epsilon. And also I have some inequality with involving q. So e to the minus 1 over plus 1 over n times t is also smaller than it. Thank you. Because q is an q is an integer vector, so the absolute value is some large integer, and then you shrink it with e to the minus 1 over t, 1 over n times t, and it becomes smaller than t. So let's just move things to the other side and raise to the power. So this means that x times q plus t to the power m is smaller than epsilon to the power m. So epsilon to the power m e to the t, and then q is smaller than t to the n is smaller than epsilon to the n e to the t. You have a minus. And then if you multiply them, so you multiply those two inequalities, you get what you want. So you get exactly the definition of being badly approximable. With this as the constant. What about the other direction? So it's roughly the same. We just need to choose the time appropriately. So assume is this okay? I mean, if ATX was not bounded, it means that there are vectors shorter than, there are times for which there are vectors which are shorter than any epsilon. Then you get this inequality. So you get here that you're smaller than any constant you want. So now assume this x times q plus p to the n times n is smaller than some constant. And the correspondence, I mean, the relation between, the expected relation between this constant and this epsilon is clear. Well, is exactly what's written. So we can now choose T such that it will shrink Q to what we want. So take T. Such that U N equals C to the N over N plus N times E to the T. And then just plug it in the inequality, so you get. So X times Q plus P, the N is smaller than this constant C to the power M over M plus N, E to the E to the So, okay, so we got these two inequalities. This and that. And by reversing the order of the arrows, when we have these inequalities, we get a short vector in the orbit. Okay, so let me draw an example. So, example, in the case M equals N equals 1, the space of lattices, okay, I'll just draw this on the board. So X is badly approximable. If and only if when you draw this picture of the modular surface, and okay, you draw this circle, whole cycle here, and you draw a line, well, this geodesic that goes 0 and ends in 1 over X. Then this geodesic is bounded. So meaning that it doesn't go very high when you bring it back to the fundamental domain, it doesn't go very high, which is equivalent to saying that you don't go unboundedly many steps to the sides, which is equivalent to having a bounded continued fraction expansion. Okay, so I guess most of you probably know this. but please ask me questions if. Okay, so we can if we think of E1H as being the same as PSL12, then this point here is the point U x times I comma I, and you act on it by 80. So maybe one of my goals in this series of lectures is to explain the following theorem. So there exists a real number, well, which is proved in paper, which is proved in a paper with Beresnevich and well, Beresnevich and Young in 2020, is that there exists a number such that all these vectors x comma x squared, x squared, x to the cube, and so on, are badly approximable. But first I want to, so there are some ideas involved in the proof of this theorem, and I want to explain those ideas in the most simple scenarios. Second, badly approximable. What? There exist. So I want to explain some of the ideas in the most simple instance. And I also want to give some background as to why this is a natural thing to look at. So maybe an immediate corollary of that is that there exists a number, there exists, well, for that x, in that case, x is badly approximable. By algebraic numbers, by algebraics. Which means that it cannot be, well, the distance between x and every algebraic number is bigger than a constant. Okay, which means that there exists some constants. There exist C1, C2, and so on bigger than 0, such that the distance between x and alpha is bigger than these constants and divided by the height of alpha to the degree of alpha. So the for every algebraic number, for every algebraic. Okay, yes, so I insist that there are constants for every degree. So, and I put here the constant which is the correct constant to the degree of alpha. So among all the algebraics from a given degree, the constants are the same, but they can vary. There exists some constants. This is here. I explain what it means to be badly approximable by algebraics, at least in my definition, in this definition, in this sense. So what is really going on here? Yes, so it's a large set. It's a full house of dimension set. What's really going on here is that there are those curves f and x, which are defined by sending x to the powers of it, and you want to take the intersection and then say something about the intersection of all the inverse images of BA. Height. Height is just the maximum of the absolute values of the coefficients in the minimal polynomial of alpha. Thank you. So, okay, maybe it's not written nicely, but I mean, you just plug in those curves in the n-dimensional space, and you want them to all of them to at the same point to be, well, yes, you want all of them to be badly approximable. So somehow you want this set is well, the set of badly approximable vectors in general is a measure zero set, but we still want to show that you can that it's large in some sense, and you can intersect it in many ways. Okay, so okay, so let me. Yes, and we need. What else to finish? Well, house of dimension. Okay, so let me start with some background. Okay, so maybe the first result is that the measure of the set of badly approximable numbers is measure zero. But this is a basic property. It follows from Khinchin theorem, for example. Maybe even it's an even more basic fact. And then the first one to realize that this is a large set was Jarnik, who proved that 1928-29, who proved that the dimension of the set of Bedley approximable numbers is 1. Okay, here there is some misuse of the notations. Sometimes this set is the set of real numbers, and sometimes it's a set of vectors. But, Amen. Thank you. This was the theorem. And then Davenport in 64 actually proved that this set of badly approximable numbers satisfies this intuition of being large. So if actually you expect that if a set has full house of dimension, then it will intersect sets of positive dimension if they are not, there is no reason that they will be correlated. So what he proved was that there exist uncountably many x such that x squared and x to the n, or for every n, is our badly approximate. So here it's not a vector, it's just all those powers of x. And he also, in the same paper, he was also asking, remarkably, he was asking this question about the parabola. So is it true? So that was his question. Is it true that there exist uncountably many x such that x squared are badly approximate? So at that time there were already algebraic constructions of pairs of numbers that its and its powers are badly approximable, but those are algebraic constructions. So he was asking about any other, and this was not known. And this result actually is very important to the story because it was exactly what motivated Schmidt to invent his game. So it's noticeable that here it's about just finitely many powers, and then Schmidt was this encouraged Schmidt to try and think of it as a game. So if the set BA is large enough so that you can construct those numbers, in order to construct a real number, you need to specify like a shrinking process of zooming in. So if you can zoom in into a number such that x is badly approximable and such that x squared is badly approximable, maybe you can do it simultaneously. And this is very similar to just playing a game. So because here those are numbers, and this is a vector. Sorry, that was not written in the most convenient way. Okay, and then Schmidt, in his 66 paper, he improved this statement actually to the following. He proved that the dimension of that set such that x squared, all of them are in BA, is full, is one, out of dimension of that set. So let me describe the game that he was playing. No, not necessarily, but you can actually deduce that from the theorem. So from the general theorem. So you can also look at the other. You can also look on any countably many curves you want, and they will have a non-empty intersection. So yes, you can look on. You can define all those. So for every finite set, for every a subset of the integers finite, you can define this FA. Well, FA of x, which gives you x to the power a1, x to the power a, and then you can intersect all of them. No, but still you can prove a stronger theorem that A inverse of BA is not empty. So let me now define this winning. Is that answering your question? There is some relation, so there is so if this vector x to the n is badly approximable, then it means that one over m right, this is bigger than 0. This is bigger than a constant. So we can deduce that q to the 1 over m and q times x to the power I is bigger than plus p. I. is bigger than a constant for every I. For some I. For some I. Okay. So at least one of them is not right. The power of Q is 1 over m. But this is an estimate which is much worse than, anyway, this is an estimate which is much worse than being validly approximate. And also, now I'm not sure. And here it's, okay. The modulus. No, you mean the product of all of them, or? Okay, I know. I'm not sure what is the question. I mean, I don't know what is the modulus. Okay. Yes, all these numbers are badly approximate. And the way he did it is by playing a game. So we can erase this. Schmidt's game. Okay, so x is some. Wait, that's not yeah, x is a complete metric space. Complete. And S is some set, some given set. Now given some parameters alpha and beta, there is a game played between two players. Let's call them Alice and Bob. And in the first round, Bob chooses ball. A ball in X, let me denote it by B0. And a radius. So it specifies a center and a radius. And then in the next turns, given Bob's last turn, Alice chooses a ball contained in the ball of Bob. So Alice chooses A1, AN plus 1. Ball under that yn plus 1, and whose radius is alpha times the radius of Bob's previous ball, which is contained in Bn. And given Alice's choice, Bob chooses Bn plus 1. I will draw a picture in a minute. So Bob chooses Ba plus 1, which is a ball around Xn plus 1 times alpha beta Rn, which is this contained in n plus 1. And this is what I call Rn plus 1. And then the game carries on, and the outcome is the limit, is the point in the intersection of all balls. And we say that Alice wins if the outcome is in S. And okay, so wins. Alice wins. If outcome is in S. So I promised a picture. So this is B0. This is A1. This is B1, and so on. So this radius is R0. Yes, and then the radiuses shrink. In every turn of alpha, the radius shrink by alpha. In every turn of Bob, the radius shrink by beta. So here are some definitions. S is alpha winning if for every beta Alice wins. Alice can win. Okay, and sometimes you say that S is winning if it's alpha winning for some alpha. So this is really the property that we want in order to ensure that winning sets will be large. So and the reason is that I mean, now it's a theorem of Schmidt. In that paper in 66, that first of all, if S1, S2, and so on are winning, then this intersection alpha winning, then the intersection is winning. So this is one. And then, okay, there is still no guarantee that a winning set is not empty. I mean, but now if X is, okay, if X is R to the K, then alpha winning implies a full dimension, full house of dimension. Okay, if X and then S alpha winning implies full dimension. And lastly, the winning property is preserved under some nice maps. So that's what Schmidt calls local isometries. So if but at least if X is 1, if X is R, then and F is some F is a differentiable. Yes. Well, I need it to be bijection. So let's say C1 diffeomorphism. And S is winning, S for winning implies F of S is alpha. So, and then this would imply the theorem of Schmidt, the theorem of Schmidt there, this here. So I definitely don't have time to carry on with all the cite references. So, but I want to show you the proof of Schmidt's theorem.
It's a lot of constant.
This will be a main point tomorrow, I think. So maybe it will come right now. So because I want to already give you the definition of another game that is that proved to be more useful for applications. So let me do that now. Okay, maybe I'll keep this drawing. So XD is a complete metric space. S is a subset. Now, given I'm going to define another game, but I'm going to keep the definition of Schmidt's game on the board. So here there is in this game there is only one parameter, which is called beta, which is going to replace what here was alpha times beta. So only Bob is in charge of. So now I call it. This is another instance of Schmidt games. So I call it Schmidt games. And the game goes on in a similar fashion between two players. The first player chooses a ball. The second player, Alice, she chooses a ball. A ball which is not necessarily contained in Bn, but just any ball of radius. Beta times Rn. And then Bob chooses a ball that avoids her choice. So Bn plus 1. Is a ball of the same radius. Which do not intersect An plus 1. Equals the empty set. And now I shouldn't cheat. So I don't want to cheat you. So it's possible that the game will not be able to continue in this fashion because okay, what is the drawing here? B0 is this, and then I should have done it with a different color, but A1 is some ball here, and then B1 is another ball which is contained. It should be contained in the previous ball of Bob. And then the game carries on. So this will be A2, and this will be B2, and so on. And it's possible if you play the game not on the, well, if the parameter beta is too large, or if the space is too sparse, then it's possible to exhaust all options. So in that case, I just say that Alice wins. If the game stops, Alice wins. And that's a manifestation of the fact that Bob was allowed to choose. Did I say this? I didn't say this. This is actually part of the. Okay, this is stage 0 of the game. Bob chooses. Bob chooses this B0. This beta. So if he was too greedy and he picked a large beta, then he's to blame, and he can try again and choose a smaller beta. So if the game stops. And then Bob can so now there is a similar definition, right? So the game a set is called okay. This game I should call it. This game was defined by McMullen. If the game stops, then possibly Bob can choose a smaller beta. So a set is winning. A set is winning if no matter what Bob does, Alice can win. So if he can choose a smaller beta and the game will not stop, then it's still meaningful. But if for every beta the game stops at some point, then it means that the space is not large enough. And then it means that winning sets will not be large actually in that kind of space.
So that means that if you stop, then starts again and keeps going.
Well, okay, let me finish. McMullen, he called it the absolute game. So to answer Anish's question, S is absolute winning, absolute winning. If okay, I should write here, no matter what Bob does, no matter what Bob does, Alice can win. Okay, this was also supposed to be here. So Bob can choose. In that sense, the game can be carried on from the beginning. So in that sense, Alice should be able to win no matter what Bob does. So, and then this will guarantee that the set is large. So the reason it's called absolute is because it doesn't involve a parameter. And this is very useful here in this property. So it gives a much more general invariance under maps. So then in particular, this will be true in general. So if S is absolute winning, then okay, this is also true in general for alpha winning sets, but then the constant will be different. So if you want to insist that to apply this theorem in auto decay, then the constant will not remain the same. Then you will not be able to take intersection. You will not be able to apply this property. Okay, so let me try to give the proof that badly approximable numbers are absolute winning. Any questions? If it's alpha winning, then it is alpha prime winning for every smaller alpha. And also, if the set is absolute winning, then it's alpha winning with a half, which with alpha equals half. So, okay, maybe a remark or a theorem. I guess that's a theorem of McMullen that absolute winning implies 1/2 winning. Okay, maybe with every constant that is smaller than 1/2, that's McMullen. Then the fact that it's 1/2 winning, then it's just a matter of trying to prove this. It's not. It's a manipulation with the sets. It's true. Okay, wait, I want you to ask this again, but that is true in RK. Yes, if the space is not large enough, then absolute winning sets can be empty, but winning sets are still dense. So, yeah. Wait again. Can you ask again? Yes, this is also true. So if it's winning, if it's absolute winning for beta smaller than beta 0, then it's absolute winning in that definition. This is what you asked? So, okay. But this is, I'm thinking if I need this, or maybe I need this, so. Okay, maybe I don't need this. But if you're if Alice can win the absolute game, when Bob chooses arbitrarily small betas, then it's as good as being allowed to choose any beta smaller than 1. I mean, then it implies absolute win. Okay. So now proof. Now a theorem. EA as a subset of R is absolute winning. Proof. So the proof is really Schmidt's proof, but apart from the fact that he was not playing the absolute game, but he could have played the absolute game. So if he had defined it, so okay, so maybe I should say that this was defined by McCullen in 2008. Then. Okay, so. So we need to show that Alice can win, right? So Bob starts, right? So Bob, assume Bob chooses some beta. Okay, let's assume it's smaller than 1/3, because otherwise the game can end if you play on the real line, and if you play on the real line, and you're in the interval, and then Bob chooses 1/3 of the center of some ball. Alice chooses the center of a ball, then Bob cannot continue playing. This is just a remark, but this is just if beta is smaller than 1/3, then we don't need to care about whether the game ends or not. So that's not a problem. Chooses some beta and some B0. Now Alice, so define some constant C. Okay, without loss of generality, we can assume that R0 is small. So R0 is smaller than, let's say, beta over 4. I think this is the correct number. But since beta is already chosen and R0 was chosen by Bob, but we can just, Alice can just decide that she doesn't do anything until the balls shrink to a certain radius, which is okay by the rules of the game. I mean, she can choose whatever, she can just play arbitrarily. Then define C to be, I think, R0. I mean, she's going to force the game to end in a badly approximable number with a constant which equals to this R0. So let's do the inductive step. So assume Bn. Assume Bn was chosen such that for every rational number whose denominator is smaller than beta to the power h, I think the denominator square should be smaller than beta to the power h, and p, an integer. The ball around this rational point is doesn't intersect BH. So this will be like a success, right? This will mean that Alice and as the game goes on, Alice can avoid those neighborhoods of rationals. Minus, thank you. Thank you. H. And in my notes, I denoted it by H because I have N for the dimension of the space. But now it's N, so let's stick with N. And then try to do the inductive step. So here is a claim. There exist at most one rational P over Q, well, P over Q with Q squared smaller than beta to the power minus N plus 1, which intersects for which the correct ball of radius constant over Q squared intersects BH plus 1, BH, BN. Thank you. Okay. And then this will be clear what Alice would do. Right? She will choose that ball. At least she will choose a ball that will contain this. There is R. Hopefully, the radius of the ball that Alice chooses is beta to the power n plus 1 times R naught. And hopefully, it will be bigger than this constant over Q squared. So this is one of the reasons that the parameters are made like this. But let's do first thing this, let's prove this claim, proof of claim. Assume that P1, P2, P1 over Q1 and P2 over Q2 are, well, satisfy this star. Then, yes. Both. Satisfy, yes. Both. Then what can we say about the difference between them? So on one hand, they are not the same. On one hand, the difference between them is bigger than 1 over the product of the denominators. And on the other hand, the difference is bounded between, okay, which is bounded by, okay, since Bn satisfies this property, and they intersect Bn, they must not have denominator which is smaller than beta to the minus n. So this is 1 over. Okay. Is there a way to write it without 1 over? Beta to the 2n, right? Minus 2? No. Beta is small. This is small, but not too small. Without the 2. Thank you. Beta to the n, and then this is okay. This is the picture. P over Q. This is Bn, and this is maybe P over Q, and this is P1 over Q1, and this is P2 over Q2. So the distance between them is not more than this radius and that radius and the length of Bn. So this constant over Q1 over Q1 squared plus this constant over Q2 squared plus 2 times beta to the power n R0. But now I have the other inequality about the size of the denominator from above. So this is also bounded from above. This is bounded from below by beta. Wait, I was doing something wrong. So here I should have +1 because the Q squared is smaller than that. So 1 over q squared is bigger than that. Okay. And this is just a property that Bn satisfies, but it's not. Those points cannot satisfy that one. So there's, and here I have actually beta to the n. So this is 2 times c plus r naught beta to the n. So this is 4 times r naught beta to the n, and if I chose r naught correctly, this is impossible. Okay. So it's impossible, so we prove the claim. So there is only one, and we just need to make sure that the constant over q over the denominator over its denominator squared is smaller than beta to the n plus 1 times r0. Oh no. Oh no. I want to keep this. So let's go to the other side. So just make sure, so Alice can choose. For example, so if it exists, right? So Alice can choose this ball around this unique rational with radius beta to the n plus 1 times r0. Okay, and we just need to make sure that beta to the power n plus 1 r0 is bigger than, so we need to be bigger than or equal to a constant over q squared, right? We want her to remove that neighborhood of this unique rational if it exists. And let's see that we really have it. So it will be implied by if this was bigger than something bigger than that, right? So beta n plus 1 r naught is bigger than something which is bigger than the constant over q squared. So this r naught goes away, right? The constant is the same. Okay, this is just what we have, right? U to the minus u to the power 2 is smaller than beta to the power plus 1. Okay, we have it. So I want to start to wrap up what we did, and the main reason I wanted to show this today, before I show more complicated proofs, is that there has been tremendous progress or achievements in the last decade with proving that those badly approximable sets are large, and all of them. So the first was Badziakhin, Poynton, Vellani The first, which I'm referring to, was this Badziakhin-Pollington-Vellani proof of Schmidt's conjecture, which I didn't have time to mention, but I will mention it tomorrow. And since then, proofs became more and more sophisticated. And that was, so when the proof of Schmidt's conjecture appeared, that was roughly when I started my PhD with Barak. And he wanted to understand that proof. He asked me to explain it. And it took me a lot of time to understand it because the construction is very involved. And the reason it's involved is exactly because they are looking for this analog. They are looking for an analog of of this claim, right? Which okay, for planes, for higher dimensions, this is just called the simplex lemma. So they are looking for the analog of this claim, and they are looking for really trying to find those dangerous sets and follow the computation and follow them and try to show that they are negligible. They are there are not too many dangerous sets. But the situation becomes more and more involved because let's say you want to play on the line, on a curve. Then you need to avoid all those rational lines. You want to show that the set of badly approximable things on the curve is small. You need to avoid all those rational lines that appear from this. You know, when you put the rational numbers in the unit square, you immediately start to see that they align on lines somehow. So these are all the rational numbers with denominators smaller than 3. Let's try another one. I don't know where this is getting me. But anyway, they sit on lines somehow, and those lines you don't have control. So you don't have control over the line. You have a control over the coefficients that define the rational line, but you don't have control over the slope of the line and the way it meets the curve. And in the other situation, when you want to do it for Schmidt's conjecture, which means that around every rational point, you put instead of putting a box, a square, you put a box, which shrinks faster in one direction than the other. And then again, you have this phenomena that you do not have control. You have control on the size of the coefficient, but you don't of the coefficient of the line that the rational points are aligned on. But you do not have control on the slope. So if the slope is close to this, then a small neighborhood of the line will remove the whole set. If it's like this, then a small neighborhood of a line will not remove, or maybe you'll need it's the other way. You will need a much larger neighborhood in order to remove the obstacle, the dangerous set. So trying to follow all the computation and taking into account all those possibilities is a headache, and you need someone very smart to do this. And I was really hoping that there will be an easier explanation that normal people can also understand. I think now there is. So I think there is an easier explanation. Hopefully I'll be able to tell you about this. So maybe I'll stop here.
Any questions, please?
You didn't quite say what Schmidt's conjecture is.
Schmidt's conjecture says that bad BAW intersection with BAW prime is not empty, where BAW is what happens when instead of equal weights in the flow you take e to the W1t, e to the W2t, e to the minus t. So W is a vector. W is W1 plus W2, and for our purposes, well, W1 plus W2 equals 1. And then you look on bounded orbits of this flow instead of the one with the equal weights, and you want to show that there is. So you have this picture here of the space of weights. And you can flow in 2 different directions. And you want to show that you can be bounded in both directions. So this was Schmidt's conjecture.
Any other questions?
So I have very basic question. When you define Schmidt game, you write the set S, which is then you define alpha winning set as S, right? So are there any necessary conditions for S to be alpha winning, like sort of dense set it should be in the space?
For sure, there will be dense because Bob can choose the ball the first ball wherever he wants.
Yeah.
Well, there was a theorem of Schmidt that says that the dimension is 1.
Yeah.
So that as well.
Okay.
It's gotta be quite large because it's invariant. This notion is invariant under maps.
Okay.
And,
Okay. So
and it has this countable intersection property.
Okay. So can we think like can Cantor set or these kind of sets can be winning for some alpha or beta? We can define like that.
Say it again.
Like, can we say that Cantor set or Cantor ternary set, these kind of sets can be, like you give an example for
the middle
badly.
thirds Cantor set?
Yeah.
Okay, that is not winning because it's not dense.
Yeah.
But, right?
Yeah. Okay.
But you can play the game on that set. So you can restrict your X to be
Cantor set.
Cantor set.
Yeah.
And then you get interesting things happening. So we'll talk about this.
Yeah. Okay. And one more question that if I say that I have sequence of beta I, which is converged to beta, and for every beta I, we have sort of alpha I. So can we, and beta I, alpha I have winning sets. So can we say some thing like there exists some alpha for this limiting beta so that winning set can, like Alice can win for that alpha beta game? Like, okay, should I repeat?
Maybe for some specific values of alpha and beta, but not in general. There is no. In general, this notion of alpha beta winning is quite mysterious still. So it's not a very robust phenomenon. So you can be alpha beta winning for some alpha and beta, and not alpha beta winning for some alpha prime smaller than alpha. So the property that is quite robust. What's going on? The property that is quite robust is alpha winning. So if you're alpha winning for every beta, then you can say something. If you are alpha beta winning for particular alpha and beta, then it's not very useful.
Yeah. Okay, thank you so much.
So this is like, again, her question that I am putting it in a different manner. So if you have alpha I, beta I winning set, right? And you have, like, we are talking of convergence and we have alpha I, beta I converging to some alpha beta. Would that alpha beta be also winning set?
I don't know. I don't think so. I don't think so.
No.
There are some works on this, but
Okay. Yeah, and I'm just trying to put her question in a better way. Okay.
this is an interval. This is an interval. This is an interval, right? It's a closed interval, actually. Yes. So maybe this is close to what you were trying to ask. So if you are alpha winning for every alpha, and you have, but if you're alpha winning, it means that you're alpha winning for every beta, and you have a sequence of alphas. Then it is true. Then you will be alpha winning for the limit, but you need to be alpha beta winning for every beta. This is exactly, there is some paper of Kleinbock about this. So this is an interesting phenomenon. There is some nice set of alphas, alpha and betas. I mean, he drew this diagram for some specific sets, and it's an interesting diagram. Look at. Yeah, in general, it's not a very robust property. This is one of the reasons that it's easier to play the absolute game, and also you have just one parameter. And in most situations, most natural sets that are winning are actually winning because they are absolute winning for some game. Maybe not this specific absolute game, but there are versions of absolute games in which you can avoid not specifically neighborhoods of points, but neighborhoods of hyperplanes or neighborhoods of other sets. And then most natural situations that appear in dynamics or in the Aravinda approximation, the reason that you are alpha winning for some alpha is that you're actually absolute winning for some absolute game, for the right absolute game. So you have some description of the sets you need to remove. So here it was an interval, but in general, it will be something.